It is amazing what we've accomplished with rockets, but to bring people to space cheaply, we need a highway to the heavens, and recent progress on space elevators may finally be bringing them to a future near you. Space elevators are a topic that needs no introduction. As we all know, they're an immensely strong rope down from orbit that you can climb up to space on, but there's a lot of details that tend not to get covered, like how you actually build one, how it can get used for traveling to other planets, or even moving around hours faster. Does it actually have to be built at the equator? Do we have materials besides graphene to build it from? How big is the elevator? How massive is it? What happens if it falls down? How big are the climber cars that go up it? How many people can it carry at once? And of course, the answer depends not only on a lot of the technical specifics we won't be able to narrow down till we build some prototypes, but also on how big an elevator you want to build. One twice as thick can carry twice the cargo, assuming it is made of the same substance. And we'll be talking about those possible substances, particularly carbon nanotubes, graphene, and hexagonal boron nitride as we go, including the idea that we might make a tether that was graphene on the inside and boron nitride on the outside. We'll ask how much we can send up one elevator at a time, and also what they look like, and even what color they are, though many like to think of them as green, like Jack's beanstalk, at least in an ecological sense. They are a green road to space, since they are made of carbon rather than releasing it as many rockets do, and you need many rocket launches a day to ever let space travel get to the point that the typical person might be able to do it, whereas with space elevators, we can build thousands of them if there was sufficient demand for cargo and people want to make the climb to space. We are also going to discuss how we climb one of these elevators today and what the climber might look like. These tethers may come in many shapes and sizes, but our default one for today will be a tether that is just under 1,000 tons, 100,000 kilometers long, averaging about 10 kilograms per kilometer, and is a meter-wide ribbon 12,000 atoms thick that a climber goes up, itself weighing about 20 tons, of which ideally most will be payload, but by default we'll assume a half and half mix, 10 tons of climber and 10 tons of people or cargo, though we'll also consider a more optimized 14-ton cargo to 6-ton body version. This version though lets us move 170,000 tons of cargo per year up to geostationary orbit and beyond, and that can include more tethers to be moved up there and dropped down to carry even more cargo. It's truly transformational technology, and we'll only be able to skim over the impact it has on Earth, which goes far beyond getting off Earth. We've looked at space elevators before, about 8 years back, but we are also on the roughly 8th architectural generation for space elevators these days, so there's been a lot of changes. I want to note from the outset that a lot of these updates for today are from articles by ISEC, and not me, a different ISEC, the International Space Elevator Consortium, a longtime partner of the National Space Society, which I still have the great honor of being president of, and a lot of its members are friends. There was a conversation on the matter earlier this year that made me feel it was time to return to the topic of space elevators for some updates, and some deeper looks at both the engineering and the strategies we would use for employing them, both how we should and if we should. I also later sat down with some of their members to review the script, and unsurprisingly, it got even longer as we thought up excellent new points to make. Even as I was prepping this episode, I found there was more material on the topic than I could squeeze into a single episode, even a long one like today's. So we will revisit this topic again soon to look at more in-depth aspects of space elevators. And today's episode is accompanied by a poll to help pick which subtopic to examine in more detail: the material science of the elevators, using them as an interplanetary launch system, or cosmic railways, their actual building, operation, and economics, or to consider their wider impact on society. So don't forget to vote in that poll over on the channel's YouTube community page. Additionally, many of our parallel topics like skyhooks, rotavators, mass drivers, orbital rings, and launch loops probably need a deeper and updated look. For alerts when those and other episodes come out, make sure to hit the like and subscribe buttons, and grab a drink and a snack, because we've got a lot to cover today. Now, odds are good that if you're watching this episode, you already know what a space elevator is, but in point of fact, the idea only settled into its modern form in the 1990s when we started discovering super strong carbon allotropes like carbon nanotubes. The concept already existed before then. Indeed, we see it in ideas like the Tower of Babel, Jack and the Beanstalk, and many variations of the World Tree or Cosmic Tree or Axis Mundi in variations of ancient tales. Yggdrasil from Norse mythology would be an example of those, and the Rainbow Bridge for that matter. Much discussion of space elevators and parallel constructs draw on these four names, and another common name for a space elevator used to be a beanstalk, but before the 1990s, we only had 3 ways we could imagine building one, and none were up to the task. We had classic compressive material you build a tower out of, and these rely on compressive strength. How strong a material is in the context of stacking weight on it, compressing it before it breaks. Konstantin Tsiolkovsky, also known for the rocket equation, discussed the idea of a space ladder way back in 1895. These are now generally known as a space tower, where they rely on compressive strength, with elevators now being those built on tensile strength, how well a material can handle being placed under tension before breaking, like hanging a weight down from a rope and adding more weight until it snaps. In the past, the term elevator generally applied to both, along with the concept of active support structures, such as the space fountain. These are ones that are not based on material strength but active effort to keep aloft, much as a piece of paper might float over a heat vent on the floor. If it falls down to the ground, it stops falling further because of the compressive strength of the material below it. If we hung it from a cord from the ceiling, it would be held by tensile strength, and if we added more and more papers, the tension in the cord would rise until eventually it broke. Our focus today is going to be the tensile strength version, as that is generally what space elevator means nowadays, but we have looked at alternative approaches relying on compressive strength or active support. See our Space Towers episode for details on those. Yuri Artusanov also called them a cosmic railway when developing the idea in the 1960s, and an underappreciated part of the space elevator is that it's not just for getting into space, but it actually lets you launch at high speed to other planets fuel-free. Another thing that's become synonymous with space elevators is rising to geostationary height, but in point of fact that's not the job of all space elevators. It's specifically the tensile versions that have to go at least that high, and what's more, geostationary itself is not really what we are aiming for, but higher. As to why, it's because that's where we want to hang an elevator down from, which again is why it's critical to the tensile strength variety that hangs. But in broader terms, it comes down to getting up into orbit and how your speed rises for a given angular velocity the wider your turn radius is. In non-technical terms, imagine a bike wheel a foot in radius, or 2 feet in diameter, or 2 pi feet in circumference. If I spin that 140 times per minute, or 140 complete revolutions per minute, 140 RPM, then the edge of that tire is going 10 miles per hour, and a bike sitting on a pair of tires doing that would, ideally, be moving at the same speed on a good low-friction bike path. Its tangential velocity is 10 miles per hour. If I double that rotation rate to 280 RPM, I will double that tangential speed. But if I build my wheel twice as wide, a 2-foot radius or 4-foot diameter, my wheel circumference is also now double, and thus its tangential velocity at 140 RPM is also 20 miles per hour, same as the smaller wheel moving twice as fast. Angular velocity is how fast you are turning around. Tangential velocity is how fast you'd be going if you got released from that spin, like a stone from a sling. Now, Earth's radius is about 4,000 miles or 6,400 kilometers, and you need to be about 100 more to be above the atmosphere, the lower edge of what we call low Earth orbit or LEO, which is where very nearly every satellite and spaceship are or were. Earth rotates once a day. In fact, actually once every 23 hours and 56 minutes, not 24 hours, as it also orbits the Sun and moves about 1 degree around the Sun each day, and needs to spin just a little further around to point the same piece of Earth back to the Sun. There are 1440 minutes in a day, though again, only 1436 of those are needed for one complete spin, and so Earth's rotation rate, or angular velocity, is 0.000696 rpm, which is very tiny, but Earth is a very large wheel, so our tangential velocity at our surface ranges from basically zero at the poles to a maximum at the equator, where the wheel is widest around our axis of spin, of about 1,000 miles per hour, or 600 kilometers per hour, or 460 meters per second. You do not need to memorize any of those numbers either. There's no pop quiz at the end of the episode. And in truth, we're mostly covering it to stretch those mental muscles having to do with speed and rotation. We will be switching back and forth between metric and imperial fairly casually today, and I encourage you to be comfortable with both, as space elevator research tends to use both. In truth, we do this in most episodes in deference to the audience being split about evenly into three camps: imperial, metric, and those used to both. I generally encourage folks not to get stuck on any single system of measure anyway, for the same reason it helps to be at least a little familiar with a couple other languages, especially if you plan to be a scientist or engineer, where we tend to have a lot of different measuring systems, and in physics in particular, we've got dozens, and for good reasons. Standardization is very handy, but can also be a mental trap. It makes you think if you want a very tall structure, you must have a very sturdy foundation. It makes you start thinking we need to measure days in kiloseconds, 86.4, or the distance to stars in terameters instead of light years, which would be just fine. It's 41 terameters to Alpha Centauri, for instance. But stellar distance and that connection to light speed and the huge time intervals is pretty conceptually important. Again, we'll just stretch your mental muscles today, as we get ready to think about trying to stretch a tether all the way up to space, and then a long way beyond. People don't think about it very often, but we generally try to put our satellites as low to Earth as we can without the atmosphere dragging them down. But we also would generally like things to stay more or less in the same spot overhead. Unfortunately, the orbital velocity just above our atmosphere is about 8 kilometers per second, or 5 miles per second. As you get further from Earth, the gravity decreases and requires a lower tangential velocity to stay in orbit. A lower tangential velocity is combined with a wider radius or circumference in the circle you are making around the planet as you get further away, so that period it takes you to complete an orbit or revolution keeps rising. Eventually you get to a place where you orbit Earth once a day, and if this was over the equator, you would appear stationary in the sky, as the planet and you both spin in lockstep. We call this geostationary, and it occurs 35,786 kilometers, or 22,236 miles, above Earth's equator, or at a radius of 42,157 kilometers, or 26,195 miles from Earth's center. Keep those differences in mind, as people tend to accidentally interchange the two while running their numbers, especially when trying to figure out a space elevator for other planets or moons. Venus, for instance, rotates so slowly that its geostationary height is actually beyond its own Hill sphere, the volume of space around a celestial body where its gravity dominates, and thus it cannot have a stable geostationary orbit over 1,000,000 kilometers away, as the Sun's gravity now dominates the orbital mechanics there. Neither can our own moon for the same reason. That geostationary height is well inside the range at which Earth's own gravity has become too big a factor. For this reason, space elevators on other bodies can get trickier, and we did a whole episode on lunar space elevators there, which interestingly we usually imagine coming up from the poles of the moon rather than the equator. You can also have geosynchronous orbits, same period as geostationary, but not over the equator, so they don't stay fixed in the sky and will rotate around a given spot, rather than sticking to that spot, typically in what we call an analemma, a figure-8 pattern, though one where one of the loops is much wider than the other and generally stretched tall, based on the latitude of the viewer. The Sun will also move in an analemma over the course of a year if you were to pick a time of day to mark its position, say noon or tea time, and just plot that every day at the same time for a year. It's not geosynchronous in terms of its orbit, but amounts to the same thing as Earth revolves while orbiting it. If Earth orbited perfectly circularly around the Sun without axial tilt, we'd see the Sun at the same place in the sky at the same time of every day too, quasi-geostationary I suppose. Of course, none of these can have a geostationary orbit except Earth, geo meaning Earth, but we will use it as a general term for any world rather than mucking about with terms like lunar-stationary for the Moon or aerostationary for Mars, and the wider term is a Clarke orbit from Arthur C. Clarke, who was a scientist, not just a sci-fi writer, and who proposed using them for communication satellites where they can hang over the same place all the time. The problem is that distance is 100 times further from Earth's surface than normal low orbit, and thus requires more energy or focus to reach and introduces real signal delays. Geostationary is also not where we really want our space elevator. If you hung one down from here, it would just fall down. A space tower can be of any height and do its job, but if you step off one you will end up falling down to Earth unless you're at geostationary or higher, because all its height till then, while moving way faster in tangential velocity than Earth's surface, is still below orbital speed for its height. You could apply some rocket fuel or zip down a launch or runway above the atmosphere, but otherwise you will fall. And so would that elevator if it only went to geostationary, because only a tiny piece of it would be there and the rest would be tugging it down. Thus, if nothing else was holding it in place, it would fall toward Earth. Now above that height, even staying fixed with the ground, we'll actually need to move around Earth faster than orbital speed for that distance. As such, if nothing was holding it in place, it would fly away from Earth. We hang our tether from geostationary, but we hang it in both directions, up from geostationary, where we'll pull on some station sitting at geostationary, and down from geostationary to the equator, where it will pull down. We keep things stable by balancing these two forces. Imagine for a moment a tether 100,000 kilometers long, about 60,000 miles, and spinning around Earth daily. This tether is moving at a tangential velocity of about 3 kilometers or 2 miles per second, 11,000 kilometers or 7,000 miles per hour at geostationary. Very fast, but actually much slower than normal low-orbit satellites. Step off here and you just float, as you are moving at exactly orbital speed for this height, and step off it at just above the atmosphere at low orbit, and you plummet rather fast, as you would only be moving about 470 meters per second, only about 6% of the speed needed to orbit there. But at 100,000 kilometers from Earth, that speed is up to 7.73 kilometers per second, 17,300 miles per hour, about the speed needed for low orbit, only you're way up in the highest of orbits now, and gravity has grown far weaker. Indeed, is about 300 times weaker than our planet's surface. Orbital velocity is just 2 kilometers per second, and escape velocity just 2.7 kilometers per second. As such, at the end of that tether, you have a remarkable 5 kilometers per second of extra speed beyond what you need to leave Earth behind. So you can let go of this tether and fly out at a speed that would take you to Mars or Venus after a time. Indeed, with good timing, you could release at a given height to take you to either without need to burn any fuel for the trip. Which would be great for freight, but I think we'd still use faster speed for passenger liners, who simply save a lot of energy by leaving here. So the point of a space elevator isn't really to get to space, it's to get to high speeds for free, or for no rocket fuel anyway. 100,000 kilometers tends to be the default for tether length. It's not entirely arbitrary either, it works well as a length for giving us both the center of mass and the center of angular momentum. Since longer gives you a higher launch speed, there's no real reason to shorten it, but you could instead have a counterweight station of large mass sitting somewhat above geostationary height. You probably would have a station up there, it's just handy, but the interplanetary launch aspect is too valuable to bypass unless you have tons of tethers connecting to the same station, which indeed you might. This isn't just for getting to deep space either, beyond Earth's area. You could release and apply some rocket fuel to achieve stable orbits at different heights of that tether, but you could also let go partway up and fly around the planet. Climbing to 1,000 kilometers or 600 miles in height and dropping is a very good way to cover a lot of distance, as you leave it at 1,200 miles or 1900 kilometers per hour, much faster than a plane, and you would pick up a lot of speed as you fell until you hit the atmosphere. Your downward speed would have leapt up to almost 4 kilometers per second, or about 14,000 kilometers or 8,700 miles per hour. As you reach the atmosphere, and your wings and drag should let you translate that into a decent sideways speed to glide pretty much anywhere on the planet a lot faster than we travel now, and without using the onboard fuel. Indeed, you are climbing and only using about 8.5 megajoules per kilogram, or about 8 megajoules a pound, which translates to about 4 kilograms per liter of gasoline or 30 pounds per gallon of gas in terms of energy. That generally implies a fuel cost of a person and some luggage, at least for today's price of gas in the US, at under $30. Not bad for transportation costs anywhere on planets and in a few hours, though this is likely being done with solar panels hanging off the tether, not gasoline, and probably hanging at geostationary. Though it depends on what you're building that tether out of, and you might be beaming energy down to climbers or crawlers along the way. So that's the real use of space elevators, and I felt we need to go over the purposes and mechanics in some detail because it tends to just get listed as this big object for traveling to space, and that leaves out a lot of the core details that really matter as we try to build one and ask why we would. Now, we were talking earlier about tensile strength, and the idea is that we want a material strong enough to suspend climbers, crawlers, or cars, whatever we choose to call the airtight pods moving up and down these space elevators, without that tether breaking. Our problem is these tethers are very long and heavy themselves. Every material has a tensile strength. Steel is obviously a lot higher than tissue paper, and it also has what we call a break limit or breaking length, which is how long a given material can be before it would snap under its own weight. This length is calculated by taking the tensile strength of the object and dividing it by its density and the strength of gravity. For a hemp rope, that tensile strength is about 550 megapascals, divided by a density of 1480 kilograms per cubic meter, about half again that of water, and by gravity strength on Earth of 9.8 meters per second, and works out to be about 38 kilometers or 23 miles. A rope longer than that, or with any imperfections, or to which we attached even a feather more of weight, would snap. Most materials we think of as super strong, in terms of tensile strength, can handle somewhere between tens of kilometers to low thousands of kilometers. Even the low end of that is pretty impressive, and misleading too, because it needs to be perfect, and in practice it won't be, and thus will break easier. But tens or even thousands of kilometers wouldn't seem sufficient when what we actually need is tens of thousands of kilometers of length, all the way up to geostationary. Distance beyond that counts separately and will go against the centrifugal force of that extended whip section, not gravity. Graphene's tensile strength is 130,000 megapascals, a few hundred times that of hemp rope, and has a density of 2,298 kilograms per cubic meter, a little over double that of water. That calculates out at 6,000 kilometers or 3,700 miles. This is the strongest stuff we know of, and again, geostationary is about 6 times further than that. And also, again, that assumes perfect manufacture of a single long cord, and we haven't gotten to anything like that kilometer scale for graphene yet. Elon Musk noted back in 2015 that until we got carbon nanotubes longer than a footbridge, he didn't want to be asked about space elevators, and the record set a couple years before that was half a meter, so I don't view that as a scornful comment, just a realistic one, that we had to work to do before any serious practical engineering was worth putting together. We haven't moved that needle, though we have gotten good at growing 4 of them up to several centimeters in length each instead. You can make a rope longer than individual strands are, of course. It's not as strong, but much as you can spin wool, the relatively short hair on sheep, into long cords, you can do that for any other material at a decreased strength. You can also stitch together smaller sheets of graphene to make a longer cord. It's still weaker than the ideal amount and by a good chunk. And that ideal amount is still, again, 1/6 the length of geostationary. So we need a stronger material, right? Well, it sure would be nice, but we've got 3 caveats. First, Gravity weakens as you get further from Earth, and the braking length of something on Earth is higher on, say, Mars, where a space elevator is a lot easier to build. But for Earth, this means a tether twice as far from Earth as its surface is, where gravity is down to a quarter, has 4 times the braking length, and at thrice as far away, 9 times the braking length. So in reality, only the bottom of that elevator tether is really doing most of that straining. Second, I mentioned that the sections above geostationary are mostly under the pull of centrifugal force, not gravity, though gravity has hardly shut off there, just gotten much weaker, while the centrifugal force straining away from Earth has gotten much stronger. But much as gravity toward Earth is still working above geostationary, centrifugal force away from Earth is still active below. That means some of your weight load is being taken off by centrifugal force in the opposite direction. So if we could find something even just a little stronger than graphene, and that we could mass produce, a space elevator would be child's play. But graphene can still work, and this is our third caveat. Braking length assumes a rope of constant diameter, but we can taper our material instead. By making it thicker up top and skinnier as we go, we can make each chunk of the rope carrying less weight per unit of cross-section, how wide the rope is, which incidentally is not necessarily a circle. Your perfect graphene or carbon nanotube cord of 130,000 megapascals of tensile strength, and the taper ratio needed for Earth is only 1.6, 60% bigger up top than bottom. And that's by area or cross-section, not radius. Even just the next class of materials below that though, ultra-strong materials like Kevlar or Xylon, can end up requiring taper ratios of 1,000,000 to 1 or worse. More recent work on the topic with a better knowledge of graphene and practical production of it tends to put the ceiling at 90 to 100,000 megapascals for polycrystalline graphene, not 130,000. This results in a tether mass of only about 1,000 tons to a few thousand tons, depending on that final strength. Note that this is very skinny, similar to yarn, thicker at the top and skinnier at the bottom, and by the way, is intended for hanging multiple 20-ton climbers on. Graphene is very strong. One of the things we'll be discussing later in the episode is how we protect a space elevator not just from accident, but attack, and that can include cyber attacks. Indeed, for a lot of us, that's a much more likely way to get attacked than physically, and often starts with people mining and selling your personal data. Most of these data brokers are acting in accordance with the law, and thus have to take your data down if you request it, but they obviously don't want to do so they don't make it an easy process. That's where our sponsor, Incogni, comes in. They use their AI to focus on finding your information online and send automated takedown requests for you. All you have to do is sign up, give them permission to act on your behalf to delete data, then they go to work and your data goes away. You can check up on the progress and see who had your data and how detailed and risky it was considered. Incogni makes these data harvesters take your info down, and they keep doing it too, making sure that it stays down. Incogni is available risk-free for 30 days, so you can try it out and get a full refund if you aren't happy with the service. Use code ISECAuthor at the link in the episode description to get an exclusive 60% off an annual Incogni plan. Go to incogni.com/IsECAuthor and take your data back. A key concept today is that while graphene is very strong, we probably can't make it full strength, and we don't want to risk building to maximum tolerance either. Now if you drop that to 50% as, say, a safety margin, that tether leaps up in mass by almost 6-fold to nearly 27,000 tons, and Earth cross-section of 14 mm squared, not 7, and a top cross-section of 163 mm squared. Though keep in mind that even there, that's similar to the cross-section of your fingers. Pencil-wide cables tens of thousands of kilometers long are what is involved for moving objects in the car to bus scale of size and mass. That will matter when we get to discuss throughput because we can keep adding more, and once you launch the first one, you can use it to pull up the next one, then use them to pull up another, and so on. Your first one might need to be thicker than the following ones, depending on your safety tolerance. Graphene is made of carbon, which is one of the most abundant elements in the universe. Needless to say, there is no shortage of the basic material, but again, it's also the same stuff diamond is made of. So abundance of carbon does not necessarily equate to cheap materials made from it. But nobody seems too worried about the cost here, as graphene is fundamentally about the same as graphite, which is neither rare nor difficult to make. So we have reason to be optimistic on this front, especially given all the improvements in recent years in making graphene commercially. All the applications the material has tend to assure that we'll keep getting robustly researched and developed regardless of perceptions of space elevator feasibility. Tethers might be circles or ribbons or perforated sheets or many other options, but at the moment I'd say something more like a ribbon about the size and shape of saran wrap or aluminum foil. If you're wondering about color, there's still some debate on if bulk graphene is likely to be black or metallic silver with a slight blue tint. We don't really produce it thick enough yet to see with certainty. And it's fair to note that we can't have much certainty about much of anything involving it if we can't even figure out its color yet. It is also likely as not to be coated with something. Graphene is a miracle material, but it doesn't do everything better, and is a material that may have to deal with being struck by lightning, scraped at high speed by climbers, and soaked in unmitigated solar radiation. Repairing a tether is a serious concern too, and depends on how it was made. We don't really want proverbial potholes in our cable. We tend to assume it will be made from graphene, a 2D material made of carbon atoms in a hexagonal arrangement. These get stacked in layers and can actually slide over each other, or you can wrap them in a roll like we often do with paper or foils. One more promising material under discussion is graphene superlaminate, or GSL. Unlike a single layer of graphene, a superlaminate consists of many graphene layers stacked together. The layering process can involve hundreds or even thousands of layers, depending on the desired thickness and properties. A layer of graphene is about a third of a nanometer, so a billion of them stacked atop each other would only be a foot high. GSL is handy for a lot of reasons. Stacking graphene layers significantly increases the material's overall strength, making it potentially useful for applications requiring high tensile strength and lightweight properties. The superlaminate retains much of graphene's excellent electrical and thermal conductivity, making it suitable for applications in electronics and heat management, but potentially giving us ways to move electricity up and down a tether without a need to bolt on heavy electrical cable that weakens the structure. Indeed, a strong electrical cable made of this stuff would be nearly as valuable as a space elevator in its own right, since it would allow us to dump untoward amounts of electricity down from space without microwave beaming. And if you can't take solar panels up a space elevator, it becomes very cheap to build a space-based solar power system. Indeed, you could potentially be using the wide ribbon version of a tether and integrating a microwave absorbing mesh into that to beam power right into the line, which can also be a wire carrying current. But I digress. As usual, graphene superlaminate can be engineered to have varying thicknesses and properties by altering the number of graphene layers and the method of bonding them. This flexibility allows it to be tailored for specific applications. Another upside of GSL is that it appears to be repairable. Graphene monolayers and laminates have a limited self-healing capacity for small damage, and if you heat the damaged areas up to about 600 Celsius or 1100 Fahrenheit with an inert gas like argon, it allows the carbon atoms in graphene and graphite to rearrange. Graphite is essentially tiny little pieces of graphene that naturally occur. So you fill potholes this way, maybe by some small climber rolling over with a tank of superheated argon and graphite. Think of it like a Zamboni machine used for fixing the scratches from skates on ice rinks, only a climber fixing a tether as it slides up or down it. The ISEC paper by Adrian Nixon detailing this process, repairing a graphene space elevator tether, also discusses using gamma radiation in the 200 kilogray range for repairing defects in it. He believes larger vacancies or potholes where the carbon atoms have been removed can also be repaired with a variant of the chemical vapor deposition process where additional carbon atoms will self-assemble to fill the voids. There are basically two types of graphene. We have black powder graphene, which is getting quite cheap these days, and will likely be coming to concrete roads or bridges near you very soon, as they make concrete much stronger by adding just a fraction of a percent of graphene powder to them. Also handy since it's a great way to save money, improve road lifetime and safety, and sequester carbon. That's one of many applications of it that I discussed with Adrian while drafting this and getting updates on what they're up to at GEEK, the Graphene Engineering Innovation Center. And I am tempted to do an update episode on our impact of graphene video from some years back, just to look at all those new ones and the progress on them. But today we're interested in another type of graphene, polycrystalline graphene made by depositing carbon on a sheet of copper foil. This is done by heating methane up, which as a reminder is one carbon atom bonded to 3 hydrogen atoms, and the carbon once free will naturally form that hexagonal graphene layer on the copper catalyst and stop once it makes a layer. Handily, if you can reuse this copper sheet, it will actually be annealed by this process, and each repeat will improve it and decrease imperfections in the graphene as the copper sheet gets improved. We can now produce sheets at a rate over a meter per minute. It's polycrystalline because multiple crystals will start growing on the copper sheet and run into each other, making it look patchwork like a camouflage pattern. Those points of connection also aren't quite right, causing a slight defect which lowers strength from the 130 gigapascals of ideal single crystal graphene to something in the 90 to 100 range. As an upside, it is more tear resistant as a result of this, one of the weaknesses of classic graphene space elevators, so this helps with that. If you're wondering, we believe any effective tether strength that works out to be 60 to 70 gigapascals will be sufficient for a practical space elevator, and even 50 might do. Incidentally, the same process, CVD or chemical vapor deposition, is used for making hexagonal boron nitride, which is arranged the same as graphene, only half the atoms are boron and the other half are nitrogen. The feedstock here is borazine, 6 hydrogen, 3 boron, and 3 nitrogen instead of methane. It is unfortunately a lot more expensive than methane, but could probably be made much cheaper if we were planning to bulk produce it. Boron nitride is nearly as strong as graphene, but has the advantage of being less slippery. Graphene has a low friction coefficient, hence why we use graphite as a lubricant, not just in pencils. It's also a good electrical insulator, while graphene is a great conductor, and we can contemplate making a space elevator that was graphene with a jacket of boron nitride on it that we could run current through and which was also less slippery. You could add track of some more mundane material for things to grab onto, but besides adding weight, we have a problem of how to attach it. Let's imagine we did a ribbon of tether and picture a sheet of notebook paper with holes punched in one side of it. Those are actually fairly hard to make with a punch. A diamond drill bit will literally slip around graphene, so better to grow them with the holes in it, which might be circles or diamond-shaped or skinny slots. You could grab onto those, though it is rather like grabbing a knife, and if you put a bolt through there, the shifting of the tether and weight is likely to slice right through even a solid steel bolt. That's manageable with some ingenuity, but figuring out the best solution is likely to have to wait on actual prototypes to see what works easiest and lightest, and it may be a perforated ribbon of graphene coated in boron nitride lets you get your best grip and run power through it too. Speaking of power and friction, it's a good reminder that elevators are made of more than just the tether and graphene. We need to move power and cargo up them, and that brings up cars, climbers, or crawlers moving up this elevator. Moving down is nice too, but technically things can just drop down from space and slow using the atmosphere rather than the tether. I've already discussed how we might move power along with a tether, but we might also power them with solar, especially once above the cloud layer, or by beaming energy down by microwave. Pods, climbers, and crawlers, and cars are all common names for the vehicle moving up an elevator, or down. I would say climber is more common, though I tend to favor cars because I tend to imagine these things as large trains running up the elevator. As something totally unshocking to channel regulars, I tend to think of space elevators of a larger scale than those normally under discussion for early usage, able to move thousands of people or tons of cargo to space every hour, if not more. So how much can they move? Of course, it depends on the size of the climber and the strength of the cable, but most calculations done about a 20-ton climber design, presumably on the grounds that this parallels what a spaceship can bring up and can also allow a decent amount of radiation shielding, a bathroom, some spare oxygen tanks, and other accommodations you might get on, say, a commercial air flight. If you need 4 megawatts for this climber to climb at the desired speed, then a 100-ton climber will need 20 megawatts and a cable 5 times thicker in cross-section, or just 5 of the same cable the 20-ton climber used. And a 1,000-ton climber would need 200 megawatts and either a lot more cables or one that had 50 times the cross-section, or of a circular cord 7 times wider. By our earlier calculations, using this pessimistic version of an Earth cross-section of 14mm squared and a top cross-section of 163mm squared, one 7 times wider is now 10 cm in diameter up at Geo and narrows to 3 cm down on Earth. This is for carrying 1,000-ton climbers and massing around a megaton, so I don't feel like I'm proposing something insanely over the top, and certainly not by SFIA standards. Nonetheless, we'll cover the 20-ton version and just multiply by 50 when thinking of throughput for people and cargo. If the climber is solar powered, then it probably isn't until it gets above the clouds, and it probably only starts climbing in the morning of each day. Until then, it probably has an actual electrical cable hanging on it. A 10 to 20 kilometer long power cable isn't that big a deal in this context. Maybe it's got a magnetic coupler, and when it pops free, it shoves to the side and pops a parachute to descend as you winch it back in. Now, as the climber rises, its weight on the tether drops. Less gravity. And for those watching, I've got a graph up from ISEC's Peter Robinson showing the effective weight of the 20-ton climber as it rises in height, and gravity drops off and centrifugal force rises. They go on to look at the cases of a climber rising at 100 km per hour and 200 km per hour, or 60 and 120 miles per hour. To get to Geo at that speed is about 360 hours, or 15 days, and 180 hours, or just over a week, at the faster speed. And even with a climber launching daily, at either speed, the majority of the weight comes from the lowest 3 climbers, with the lowest climber making up 20 tons of weight, the second lowest already down to just over half that weight, and depending on the speed, the third to less than half. For our slower case, 100 kilometers or 60 miles per hour, slow freeway speeds, the highest effective weight on that tether with 17 climbers on it works out to only be about 64 tons, just over 3 times the weight of a single climber at the bottom, even though there's 17. On the higher speed, 200 kilometers or 120 miles per hour, crazy Autobahn speeds, which I always loved when I was stationed in Germany, that trip again drops to more like 8 days, and the maximum of 9 cars on it comes in around 48 tons, just over 2.5 times the weight of a single car on the ground. So faster is better for not only allowing shorter trips for people and more throughput from the speed, but lower weight on the tether too. I generally have difficulty imagining getting more than 50 people into a module of this scale, especially given that they are stuck in it for a week or two. Even 50 might be very optimistic, but if so, that's 50 people a day per tether going to space, which is more than we launch in our best year right now, and more like what we've launched in some entire decades. So my desire to do this bigger or faster doesn't indicate an immediate necessity for the thing to work profitably. Now, in theory, you could be doing a turn and burn all the way up one of these elevators, slamming up at 1G, which would double your weight on the tether, requiring it be twice as thick and make everyone inside feel twice as heavy, then flipping over halfway through to decelerate, but would take just an hour to get to Geo, not a week or two. The maximum speed reached would be just under 19 kilometers or 12 miles per second, and to be honest, I can't imagine why you bothered decelerating for the last half. Just keep pouring on the juice all the way to the terminus at 100,000 kilometers, 75 minutes later, hurtling into space at 44 kilometers or 28 miles per second. You might even accelerate faster, cranking things up as the pull of gravity behind you weakened so the extra weight wasn't crushing people as bad. No fuel was expended, though there's serious power demands there. You could also maintain constant weight on the tether by accelerating faster as you went up it, though that would seem more about comfort than efficiency or engineering, which might win as a factor anyway. Your limitation here is that while there's no air drag once you get clear of the atmosphere, you are still in physical contact with an actual tether. And while I think we could probably pull off speeds on an order of 1,000 kilometers per hour with physical contact still, allowing trips to Geo in just 36 hours, anything beyond that gets very iffy. You have to start contemplating options for hanging something like a maglev rail off your tethers to accommodate a system that has no physical points of contact between this bullet climber and the tether. This is doable. We contemplate it for mass drivers and launch loops, and we'll probably be deep diving both of those again in coming months, but it isn't inside the basic space elevator architecture. It also tends to use the same system we need for orbital rings, which are basically the granddaddy of space launch throughput, since it uses much shorter tethers that need way less strength too. But if you can mass-produce graphene, then honestly adding more throughput with a space elevator is mostly a matter of just adding more tethers. Indeed, you probably make a given elevator out of several parallel cables that a given climber can hold on to multiple of, allowing climbers to go up and down the same elevator at once, and for faster cars to pass, and for one to be down for repairs at any point. Or up, as I imagine you would do major repairs and replacement by winching them back to the counterweight station or the one at Geo. If we imagine cables running parallel like a hexagon, with each climber needing just 2 but usually holding 3, then we have a lot of safety and redundancy going on. There's a lot of options for how you move up these too. You might have them more like bike chains and just attach a car to a given link and keep your tether chain spinning up and down a big pulley. Again, multiple in parallel can help with redundancy, and there is no need for an onboard power system except for life support. Obviously, you want to build these initially as small as possible, but the space elevator does pass not only above our atmosphere's protection, but right through the Van Allen radiation belt. So more shielding and speed is good, and shielding gets proportionally cheaper as you get bigger under the cube-square law. Big tether systems and bundles also let us imagine hanging power collectors or even protective sheaths around the tether. So much depends on what the effective tensile strength you can mass produce is. Getting over 90,000 megapascals seems plausible, and that does seem to be the conservative floor, at least inside the optimistic notion we can get the stuff cheaply mass produced without overwhelming defects. If you can, then you can also bypass one big limitation on space elevators, and that's the equator. They work best there, but few cities are located there. We often consider placing them on boats or islands instead, which work well enough as again these tethers are very skinny and carry less freight per climber than a freight truck or bus, and only 1 climber per day usually. So we're not talking about a huge artificial island or aircraft carrier at the bottom. But space commerce will only benefit if we can leave directly from existing cities, especially as space elevators could leave right from the middle of a city, as they aren't anywhere near as noisy or land-heavy as an airport, let alone a launch pad. It would be plausible to have several tethers per town even, if demand was high enough. As I mentioned earlier, we contemplate lunar space elevators leaving from the poles of our moon rather than the equator, and the very low gravity there means even something like steel or aluminum works for an elevator. But an elevator connected to Earth somewhere other than the equator is going to be out of whack, since it's pulling north or south. However, let's imagine we had 3 or more space elevators departing from various locations on the same side of Earth, with at least one in the north and south hemisphere each, rising to meet at geostationary, like guy wires on a very tall tower. And in this way we can balance out the forces and also share a destination facility at the other end. Non-equatorial tethers are, like megaton ones designed for huge cargoes, not an immediate priority of this sort of endeavor. But it's not really adding that much new strain either. Keep in mind this tether is hardly all that far off vertical. Most bigger cities would be about 6 to 10 degrees off vertical, depending on their latitude. This is also a longer cable by a non-trivial amount, and one with more of that cable in higher gravity regions, since it's coming up from an angle and from a greater depth too, given that the planet's a sphere. I do not see this causing prohibitive tapering ratios if we can do 90,000 megapascals of effective tensile strength or better, or even decently worse. And bluntly, a space elevator built up from London, New York, LA, Tokyo, Beijing, or Berlin is way more attractive for funding than one built at the equator. But those will always do better on the engineering end, so equatorial land tracks and mobile islands, ships a tether can connect to and receive terrestrial freight from, will still tend to blossom, especially in early days. It also gives countries in South America, Africa, Indonesia, the South Pacific, and Australia a potential partner and subsidy for building their own, since any new elevator servicing places in the Northern Hemisphere needs its southern anchors. These are not twin cities though, you would always want at least 3 tethers. I still think mega development of space works better with orbital rings, but since we last deep dived space elevators way back in early 2017, the developments, which we only skimmed today, make me a lot more sanguine on space elevators becoming practical, and working well in tandem with orbital rings rather than one or the other. I could easily imagine that by the year 2100, every major city would have its own tethers able to send hundreds if not thousands of people, or tons of cargo, to space each day. In terms of cost, without an actual facility mass-producing the actual tethers, it's hard to put a meaningful number into play, but we do make graphene in quantity these days, and the costs have plummeted this last decade, another reason for our update. Estimates this year are putting the demand for graphene rising at 35% a year till 2030, and expecting it to get to be about $1.6 billion a year by 2030. If that's the case, I would be fairly confident the economics and R&D for the material will start making mass producing it by the ton viable, and your basic space elevator might be buildable at that point. The energy cost to move up an elevator is in the dollars per kilogram range, around 1% of what it is now, but much like with rockets, the fuel or energy is not the main cost. Much as we can't really estimate how much it will cost to construct tens of thousands of kilometers of finger-thick cable yet, it's hard to estimate the maintenance cost of it and its climbers and facilities. Any estimate, though, needs to be held in contrast not to modern space launch costs, but the throughput of the elevator. And even the baseline model offers transport for 10 to 14 tons of cargo or tens of people every day, as we explored. Scaling up is simply a matter of adding more tethers to an elevator or adding more elevators elsewhere. The cargo value is roughly an order of magnitude more per year than the average of late, thousands of dollars per ton. So assuming demand existed for more trips to space, you would fill that quickly. Indeed, I think you would rapidly see a spike in space tourism and crewed space laboratories and manufacturing, not to mention new satellites, like space-based solar or even solar shades for environmental reasons. And I should note that space elevators are a lot more environmentally friendly than hundreds of rockets each burning 1 million pounds of fuel. Also, you could potentially start hanging satellites down from tethers, changing their orbit to be much slower or geostationary while still at lower altitudes, which would seriously decrease space debris issues and also vastly increase the effective space you could deploy satellites in, and thus their quantity, since they wouldn't need so much elbow room to minimize collisions. Speaking of that, I want to take a moment to address safety concerns before we wrapped up. First, let's talk about breaking the tether. I want to emphasize 2 points. 1. Never think of it as a singular tether, or even ribbon, except maybe the very first one launched in a rocket designed for carrying up its siblings later. At a minimum, you need to just allow up and down traffic, but always assume bundles. Remember that graphene is stronger than the Kevlar we make body armor out of. And if you tried to slash a thin ribbon of the material with a knife, it would lose. You would part the knife, not the ribbon. And indeed, it is very difficult to cut even with a laser, or diamond drill. This makes it difficult to put bolt holes in them to attach other objects, but also means the space elevator is really hard to break. They are very temperature resistant too. And while graphene is made of the same material diamond is made of, as well as coal, it does not burn. Graphite, the basic stock material of graphene, resembles coal in appearance, but is quite resistant to burning. You can make graphene or diamond burn in liquid oxygen by superheating them then dumping them in cryogenic liquid, but that's a bit of a lift, especially given that only a small piece of the tether is exposed to any oxygen, let alone liquid oxygen. For higher sections, radiation is a concern, but appears to be manageable. As mentioned earlier, gamma radiation can actually repair defects in a tether, though too much will damage it. Ionizing radiation is never a friend to any material, and over the atmosphere we get more of it. Beta radiation is no concern. Alpha and neutron radiation are, as they will break bonds between carbon atoms, but these should tend to self-heal, as the ionized atoms are very reactive. You will get transmutation occasionally. Neutrons absorbed might turn nuclei into carbon-13 or even carbon-14, but this is minimal, should not impact overall strength, and I dare say if you had enough of it, you could profitably recycle the tether to extract that carbon-14 to make diamond batteries out of. See our portable power episode for discussion of nuclear batteries like that. And Earth's magnetosphere still screens us from most of the charged particles even high above Earth. We already discussed maintaining them and repairing them, and just like any road or rail track, we should assume a service lifetime for a given cord. I would also imagine more advanced elevators would begin using thicker tethers, and those with coating and hardware attached. As usual, wear and lifetime for thicker objects will do better, and I would expect that after the first generation of space elevators get going, we would see them slowly replaced with superior, thicker tethers that permitted more traffic. A ribbon can also survive micrometeor damage, as it would be like shooting a piece of paper or sail with a bullet. Damage is done, but so long as the ribbon is wider overall than needed for its load, it will stay up till repaired or replaced. Down in the atmosphere, the story is a bit different. I should note that we could profitably use these elevators even if they never touched the ground, just dangled above the clouds, and that's the notion behind skyhooks, or those dangling satellites I just mentioned. So even if we couldn't handle problems from the weather, we might still build them. I see few indications this would be a problem either. One downside of thin ribbon tether is it does catch the wind more, which puts strain on the materials, adding tension or weight to the load. Same for problems like lightning, and there's an excellent paper from 2022, Robinson and Knappmann's Space Elevator Tether, Atmospheric Wind Loading, and a Cable Lift Concept, that walks through the problems and solutions. I could probably do a whole episode just playing with the ideas they lay out there, but the one I like though is the multi-stage approach, like a circular tether lower and a ribbon shape above the atmosphere, as it acknowledges that a tether in the atmosphere is a very different animal than the 99.9% of the thing that's above the atmosphere. I've suggested before it might be a better approach to build a space tower to the top of the atmosphere and put an elevator on the top or running through the middle of one, or to have them only reach down to an orbital ring, which has its own separate tethers with different engineering for reaching in the top of the atmosphere. You might opt to hang a second tether that was narrow cords or even a different material down for the last 100 kilometers or so, and the ribbon the rest of the way up. Or maybe a winch above the cloud layer that could roll up the tether for extreme weather. The bottom of the elevator is, unlike a tower, the least important bit of it for structural strength of the elevator, as it hangs from the bottom rather than supporting what's above. All indications are that we could make a regular elevator work here anyway, it's just the multi-stage approach might be better and leave room for future innovation. Of course, no matter what we do, we have to consider what happens if a space elevator breaks, maybe by intentional sabotage, maybe a satellite crashes into one. They are not fragile nor easy targets, so while obviously of military value for an enemy, don't assume 5 seconds after a conflict begins, the space elevators all get trashed. Trying to hit a centimeter-wide target hanging in the sky with something also strong enough to break diamond, and from hundreds if not thousands of miles away, is easier said than done. And simply being in the radius of an explosion when discussing something sturdier than steel does not imply severe damage. Don't even assume a nearby nuclear strike would get one. Still, they can break, and if they do, what happens? There are some interesting fictional accounts of them, most are wrong, others are better, and my favorite is an Alastair Reynolds novel, Chasm City, which I highly recommend for the rest of the story too, but has an elevator break early in it while our protagonist is riding it. And it notes how at first nothing happens, as waves do take a long time to travel, and we are talking thousands of kilometers, and you would have both the compression wave and the transverse wave coming up, and at different rates, and the latter would tend to snap the climber sideways, possibly kicking free of the cable. We've got 3 scenarios for breaks: close to Earth's surface, in the middle, and then above geostationary, and in each case a lower section and a higher section. For a break in the atmosphere, the lower section below the cut, attached to the Earth's surface, would collapse onto the ground. For some reason, people tend to think this is catastrophic, but keep in mind we are talking about a cable or ribbon that on the bigger side of things might weigh a few kilograms per meter at most, like a heavy electric wire, and maybe less than a telephone wire. If this is a ribbon design, it will experience so much air drag that it will gently settle onto the ground, though I wouldn't want to be right under it, especially if it fell sideways on a spot, as it would be like a katana coming down unless we blunted the edges. A classic cable will hit harder, but not that hard, not like the thing is laying waste to cities or something. The upper section of the cable, virtually all of it in this first scenario, would be flung outward due to the centrifugal force acting on it, though for an atmospheric break, this probably isn't very much, and even assuming we only had one cable, not several, attached to the counterweight station, it could have some of its immense counterweight mass being taken up with fuel or ion drives, and indeed you would tend to expect a big space station acting as a port of call to have fuel on board, and spaceships nearby able to offer a tow to stabilize it. As to the cable itself, this section might end up in orbit around the Earth or drift away into space, depending on the dynamic at the moment of the break. I should note that we do have the option of adding a small detonation charge to our cables every 100 kilometers or so to let us break them into smaller fragments if we wanted. Higher sections where mass matters less could also have occasional winches able to roll their section up, so you might have a small detonation charge and winch every 100 kilometers to break it apart for rolling up into recoverable sections. In the same way, you could also make parachutes attached to the sections. And if you can mass manufacture a thin sheet of graphene, you have the ability to make very compact and lightweight super parachutes from it. The same will apply to any car on the cable that gets hurled off it. Lower ones will fall and could deploy a parachute. I already discussed the option of having cable cars designed to detach at higher altitudes to drop and glide to distant destinations. Thin graphene wings might make that a lightweight addition that otherwise was folded up to provide shielding. If you get cars in unstable orbits around Earth, then that is a crisis, but one that space elevators offer a solution for, by allowing a huge space infrastructure where tons of orbital stations and well-fueled spacecraft can be available to come to the aid of those who have been tossed upon the ocean of the night. Now, if the break occurs around the midpoint, the lower part of the tether might start falling back towards the Earth's surface. As it falls, it could wrap around the planet, potentially causing damage to large areas. But again, remember that we are contemplating a cord that is a finger width at most. Indeed, you might have several tethers running together who have plates spaced periodically to keep them from whacking into each other, with winches for maintaining tension, and a cut in a case like that just drops, say, a kilometer of cable to dangle around, possibly where some local maintenance drone that hangs out there can swing over to wind that up, or use a winch. And again, a ribbon tether is going to have huge air drag as it falls, so isn't hitting at speed. Also, while I don't want to imply a diamond-hard tether hitting things is a minor matter, any implication that even some thigh-thick cable big enough for dragging whole trains up it would cause civilization-damaging ruin is pure hype. The cable will reach terminal velocity and cut a furrow through things, and given that it probably has lights or reflectors on it, even some person with the incredibly bad luck of being under it would have a good chance of seeing and dodging the cable. And that's assuming none of the safety mechanisms we discussed were in place. Again, if you got cheap graphene, you've got cheap parachutes. Also, if you are bulk producing this stuff, then you also bulk producing concrete with graphene in it, as a powder or even as a replacement for rebar as cables, in which case, your buildings are going to survive the impact with ease. Anyway, in this case the upper section would be thrown outward into space. Depending on the exact point of the break and the resulting forces, this piece could enter a new orbit or drift away. As with before, your space station will need stabilization unless it has several other tethers attached to it, which it presumably would. For a break above this, the section beyond the geostationary point has a higher orbital velocity than is required for a stable orbit at that altitude. If the cable breaks here, this section would likely be flung into a higher orbit or escape trajectory away from Earth. Hopefully you have a robust cislunar economy and ships that move from interplanetary bases or asteroid mines, who can potentially divert to rescue anyone. On the other hand, we mostly envision using this section for launching spaceships from, so they have plenty of time to disconnect from the cable. Again, waves travel and at much lower than light speed, so nothing changes for them till those waves from the break catch up. Many might be traveling down the tether faster than the wave, or fast enough to clear it before it arrived. They could then use their existing engine and onboard fuel to divert to a different destination they can reach, or achieve a vector some rescue ship or refuel pod could rendezvous with. In this case, the lower portion is most of the cable, and the portion below the break would start to collapse toward the Earth. The section around geostationary orbit might remain in orbit temporarily, while the lower part would descend. I think you would detonate sections of the cable at this point. You would have time to externally target them if need be, and in a way that would allow segments to fall into the atmosphere or shoot out to deeper space. I would be more worried about space debris consequences of a diamond-hard tether whipping around into some space station. So again, occasional winches for adjusting tether tension that could also roll up segments into tight balls would be nice. As before, climbers detach, blowing whatever connected them to the tether if need be, and either parachute or glide down, or get rescued by other spacecraft. On average, the nearest climber will be several minutes from the break in terms of the wave traveling to, and the others further, so there's plenty of reaction time. I think the nature of commerce would tend to result in very large space stations at geostationary, your hubs, and ones orders of magnitude heavier than the tethers, likely with ancillary facilities clinging onto them. So they would be less likely to be falling from something like this than well positioned to send rescue and aid. But that's all stuff for further down the line. In your early days, a broken tether from someplace on the equator is probably built on the coast to flop into the sea. You could build it to bias to fall in one direction, and the folks on it might be SOL, but I'd still rate their odds as better than the folks on Apollo 13. Space travel and development is dangerous. We cannot reduce all the risks, especially to something new and under development. But I think we've demonstrated it's pretty safe, and I think we've also seen that the last decade of graphene development and space elevator research has moved this structure from our previous status on the show as maybe possible but unlikely to work to probably possible and maybe practical within a couple decades. As mentioned, this is not the only structure we have in our potential arsenal for reaching and developing space, and we will be revisiting many of those as we head into 2025. Until then, remember, the sky is definitely not the limit, and a time may be fast approaching when we'll ride space elevators beyond it. I mentioned earlier that a lot of the material on this episode came from ISEC, the International Space Elevator Consortium, and I wanted to thank them again for their help, both for all their published work, which you can find at isec.org, and for all their correspondence of the last months while writing this, particularly Adrian Nixon, Peter Swan, and David Brandt-Erichsen, who took a couple hours out of their time for a Q&A with me on Zoom, and even more to help edit the script. I started off drafting this episode unsure if there was really enough new material for an update, and obviously to say there was would be an understatement. We had to skim and skip a lot, even to keep this episode at just over an hour. And don't forget we have a poll running on the channel's YouTube community page to vote on which space elevator subtopic we should explore in more depth in a future episode. Speaking of future episodes, 2024 might be almost done, but we still have 2 more shows, with a look at the idea of ultra-self-reliant and technologically advanced hermits and the Fermi paradox coming up next week, and asking if the reason we don't see advanced civilizations is that they all fall apart and scatter from a lack of need for interdependence. Then we'll close the year with our predictions for the future and our civilization, as well as discussing the unreliability of future forecasting. Though I'll make one prediction for now, that we have a lot of awesome episodes coming up for 2025. And if you'd like to get alerts when those episodes come out, you should hit the like, subscribe, and notification buttons. You can also help support the show on Patreon or by becoming a member of the channel on YouTube, and you can find other ways to help out at isaacauthor.net, where we also have our big list of book suggestions for anyone looking for some good sci-fi to pass the long winter nights until our next episode. And until then, thanks for watching, and have a great week.